All right. Hi, everybody, and welcome back to MTED 110. Today, we're going to be starting Chapter 3. This is Lecture 3A. You should have just finished, or you should have finished Activity 2A by now. So this is where the chapters get a little bit switched because it's basically 2A, 3A, 2B, 3B. That's kind of how it's supposed to go. So you should have just finished Lecture 2A and Activity 2A. And now we're going to do Lecture 3A and Activity 3A after this. So let's go ahead and get started here. Chapter 3, this chapter is all about understanding whole number operations. So the previous chapter is all about our enumeration system, how we count, how we represent numbers, and how our place value system works. Now we're going to talk specifically about how to operate on numbers. Okay, so first off, the algebraic or operations and algebraic thinking domains begin in kindergarten. So we first start talking about addition and subtraction really early on, kindergarten, pre-kindergarten, in fact. Here's a standard from kindergarten. We need students that are exiting kindergarten to be able to understand addition as putting together and adding to, and to understand subtraction as taking apart and taking from. So we're expecting a kindergartner to leave kindergarten understanding that that's what addition means, putting together, and subtraction is taking from or taking apart, and we're going to talk about that today. Multiplication and division are introduced in third grade, and those we'll be talking about in Lecture 3B, and that'll be after Lecture 2B. As the grades progress, students will work with larger and different numbers, and they'll solve more complicated problems. So for example, we expect an exiting second grader to be able to use addition and subtraction within 100 to solve 1- and 2-step problems involving situations of adding to, taking from, putting together, taking apart, and comparing with unknowns in all positions. So that's a second grade. In third grade, they should be able to solve 2-step word problems involving any of the 4 primary operations: addition, subtraction, multiplication, division. They should be able to represent these problems using equations with a letter standing for the unknown quantity. So this is an interesting cognitive leap that students have to make. You might wonder, why can't they just solve things like this? Like, why can't you teach a first grader how to solve x plus 3 equals 5? That's a good question. And you should ask yourself, why wouldn't you teach this to a first grader? Why wouldn't you teach that to a first grader? Okay, now that you've thought about it for a bit, go ahead and talk out loud about it with yourself or with your group members. Okay, so this is what's interesting. There's a lot of different reasons, but the basic reason is that students are not cognitively ready to talk about problems in that way. In particular, using a letter to represent the unknown is confusing for them, in part because they're also learning how to spell and how to write and how to read. And so if you start introducing these letters that they see as part of the alphabet, and you're telling them, oh, that actually represents a number, and they're also just learning about the symbols for numbers and how those work, it starts to get very, very confusing. So in early grades, what we do is, instead of using the letter X, for example, to represent a variable, we just put an empty box. An empty box. Blank plus 3 equals 5. And the question is, what goes in the blank? And then they'll be able to fill it out, and they'll fill it out by putting their answer in there, like so. 2 plus 3 equals 5. So interestingly enough, like, our brains are not really wired to treat these things as letters in the beginning. And also, you can kind of see how this starts from an early age. What are one of the most basic toys that we give to babies to play with? Very, very first toys, almost. They're like a little box, right? And on the top of that box, there are cutouts. There's a triangular cutout, there's a circular cutout, there's a square cutout, and we teach babies to put the right shapes into the right shaped holes, right? Well, that is a cognitive skill that we can extend into our math education, because when you use this thing like an empty box, students almost feel compelled to put something in the box. And that's the exact trait that we're trying to build off of. That's why we use empty boxes instead of just letters. They're not ready for letters yet until they get to around third grade. Um, okay, so general ideas. Now, a little bit of a word of caution, and it's this, and you'll hear me say this a lot. This chapter is about whole numbers, but addition is addition, subtraction is subtraction, multiplication is multiplication, and division is division. Those operations do not change if the numbers change. There we go. These four operations have the same meaning when used with any real numbers, not just whole numbers. And so what happens is some students get into this mindset at an early age where they think that the operations change depending on the type of number you're using. Like, oh, I'm adding fractions, so the way I add fractions is different than the way that I would add whole numbers. But that's not the case at all. Addition is addition, subtraction is subtraction, multiplication is multiplication, division is division. They're the same operation no matter what kind of number you use. But people get locked into the representation of the number, the numeral itself, not the number, right? Yeah, so young learners will often think that these operations change when dealing with different types of numbers, like negative numbers. Oh, so adding a negative number is somehow different than adding any other types of number, but that's not the case. Addition is addition, subtraction is subtraction, multiplication is multiplication, and division is division. Those operations do not change. This is also why it's important for students to understand the difference between a number and its representation. We don't want them locked on the representation, we want them locked on the number and the stuff going on in the background, right? Okay, so here's a good question for you. I'm just gonna leave this up here for a second. What are these symbols here called? They're called, there's a name to describe all of them at once. What do you think? Talk out loud to yourself or talk to your group members. What do they think? What do you think those things are? What would you call those as a group? There you go. Those are called operators. So these are the four basic operators. Let me change my color here. These things right here are called operators. And they're called operators because they're a symbol, or I should say, uh, for this class, an operator is a symbol used to represent an action being performed on the elements of a set. So this is another one of those situations where you have to recognize that these symbols are being used to represent an operation, something that's going on, an abstract idea. So we're going to talk about those ideas, in particular addition and subtraction in this lecture. Um, they're also called binary operators because they operate on two different things. They operate on two things like real numbers, and they do something to those real numbers, and they spit out a new real number. So that's pretty much what's going on. Let's do this easy example. If I write something like, oh, 4 plus 5, well, what I'm saying is I'm saying do something to those numbers 4 and 5. And in this case, what I'm saying is add those two numbers, add 4 to 5. That's why it's called an operator. We're going to operate on it, right? So one thing I like to do is think about the word operator, right? Like, what do you think of when you think about the word operator? You probably think of operations, maybe you think of surgery or something like that. That's essentially what we're talking about. We're talking about doing something to something. We're talking about operating on something. Addition is like stitching two things together in some sense. Subtraction is literally taking something apart or taking something out of. It's like an extraction process. Multiplication, we'll talk about in the next lecture, and the same thing with division, but they're closely related to addition and subtraction. So we try to really, really build up a foundation for what addition is and what subtraction is. And if students develop that, then they'll understand multiplication and division even better, more easily, I should say. So what's amazing about this, and this is one of my favorite things about this course, is that the concept of an operator can be generalized in these really profound ways. And some of your students are going to do this later on. So for example, functions. Functions are operators. Do you remember these guys, right? F of x. We're not going to spend a ton of time on this, and you'll talk about these in later courses, but functions are operators because what you're doing is you're saying take some number and do something to it. That's what that f means. That little f stands for the rule. It's describing what you're going to do to the number that you put in. So that's what a function is. It's an operator. It operates on things. Limits. If any of you took Calc 1 or you took pre-calculus and you discussed limits, you probably saw this symbol, limit as, let's say, x goes to infinity of f of x equals 1 or something like that. If you've never seen this before, don't worry at all. We're not going to do calculus in this course. This is just to emphasize that you need to have knowledge on the mathematical horizon. Remember this? We focus on these concepts early on, grades K, grades 1, grades 2, so that when our students get to this, they can understand really what's going on. It's really amazing. Anyway, but these are operators. You're basically, in this case, you're taking a function and you're saying, do that to the function. So now you're taking a function and you're operating on that function itself to get some result. So that's an operator too. Same thing with differentiation. If you remember Calc 1, if you took Calc 1, the derivative and the process of differentiation is an operator. It's an operation. And integration, if you took a little bit of Calc 2, you might remember seeing this type of a symbol of x dx, right, equals some number, maybe it's pi or something like that. Well, guess what? That's an operator, and you're performing an operation. Here is the symbol for the operator. That's the symbol, and what we do is we shove a function inside. So we take a function and then we operate on it. Same idea. So we try to set kids up early on. Yeah, so like I was saying, if you didn't take calculus, that's totally fine. You don't need to have taken calculus. You don't need to have taken pre-calculus. We're going to focus on the 4 basic operators: addition, subtraction, multiplication, and division. All right. So let's see how we can begin. Oh, yeah, that's right. First, some important vocabulary. So this is very important vocabulary, using the words to, from, and by correctly. To, from, and by correctly. So here are the do's and the don'ts, you could say. Here are the here are the conjunctions you're allowed to use. You can add to, you can subtract from, you can multiply or divide by. So those are essentially the only ways you can say you're going to do something like that. You can add this to that, you can subtract this from that, you can multiply by this, you can divide by this. In contrast, here are the things that you cannot do. These are the no-nos. Do not use these phrases. You can't add by or add from. In fact, let me go ahead and use a different color here. You can't add by and you can't add from. So you don't want to say like, oh, add by 4, add by 6. That's a meaningless sentence. That doesn't make any sense. You can't subtract by or subtract to. So that's another thing. You wouldn't say, for example, you wouldn't say, let's use 11 minus 3 equals 8. You wouldn't say subtract by 3. That doesn't make any sense. That's not proper grammar, so you can't use that. Same thing with multiply to or multiply from. And this is a hard one for students to stop using, because if you say something like, 3 times 9, you might say, oh, multiply 3 to 9. That's incorrect. That's improper use of grammar. You can't multiply to, can't multiply from. You can multiply by. You can multiply 3 by 9, and you can multiply 9 by 3, but you can't multiply to. And the same thing goes for divide to or divide from. Those words don't go together like that. So I encourage you to focus on this slide and keep in mind that these are the ones you can do. Adding to, it's pretty easy, right? You can add to, you can subtract from, you can multiply by, or you can divide by. That's pretty much it. Okay, so some quick definitions. These are terms that you don't necessarily need to memorize. I'm not going to test you on knowing words like addend. But if I refer to those things and I use those terms, you need to be able to understand what I'm talking about. So you should at least have a vague idea of what I mean when I say addend and when I say sum. So in this definition, if you see a sentence like this, a mathematical sentence, the 2 numbers A and B, or sorry, 3 numbers, I'm sorry, A and B are called the addends, and C is called the sum. C is the sum. A plus B equals C. For subtraction, it's a little more interesting. D is called the minuend, E is called the subtrahend, and F is called the difference. So when we say what's the difference, we literally mean what do you get when you subtract those two? What do you get when you subtract E from D? Subtracting E from D, you get F. That's what that means. And again, like I said, you don't have to remember, you don't have to memorize these words right here. But if you want to sound really smart, you can go ahead and memorize them. Also, eventually, when you become your own math teacher and you have your own students, you're going to be referring to these anyway with your peers and your colleagues. Okay. Some properties, some important properties. The commutative property of addition. The commutative property of addition basically says that you can rearrange or you can add in any order you want, and the result is the same. That's what the commutative property says. If you take this quantity and add it to that quantity, that's the same as starting with the second quantity and then adding the first to the second quantity instead. You get the same result, and that's why I emphasize that this symbol is so important. Those are the same number. A plus B is the same number as B plus A if we're talking about numbers. If A and B are not numbers and there's something else, well, then this might not actually hold. Yeah, so that's a subtlety there, and we'll talk about it a little bit later. Yeah, we'll talk about it a little bit later when we talk about multiplication. But in general, commutativity, being able to move things around, that's a very special property to have, and we're lucky that numbers have that property, the real numbers or complex numbers. Okay, next, the associative property. The associative property is all about who you associate with. The associative property is saying that if you first add A and B together and then add C, that's the same as just adding B and C in the first place and then adding A. So in essence, it doesn't matter how you associate the sums. That's what you're going to get. You're going to get the same number both times. Same number both times. Okay, so let's talk about how to think about addition and subtraction. What we're really looking for is how to teach our students to recognize scenarios where they would know to add or subtract. So in what scenarios would we add or subtract? In these types of scenarios. Oh, sorry. What does it even mean to add two numbers or subtract one number from another? What does that actually mean conceptually? Because before we can start saying, oh, it's obvious that 5 minus 2 is equal to 3, we have to be able to explain to our students what that actually means. So here are the key ideas. Addition is just adding, combining, or putting together. And you'll see me do this type of thing a lot. This is the act of addition. Addition is taking two quantities and bringing them together. Notice that I start with two separate quantities and bring them together. That's addition. Okay, so like if I had linking cubes, right? We've got linking cubes right here. If I've got some linking cubes in both hands and I bring them together, I just added those two quantities together. So in this case, what did I have? I have three linking cubes in this hand, and I've got two linking cubes in this hand. And if I bring those two hands together, I just added. That's what addition means, okay? And let's see, that's a 5. I have 5. So if I take 3 and I add it to 2, then I get 5. So that's what addition means. That is the conceptual interpretation of addition. Now, in contrast, subtraction is the act of taking from or taking apart or removing. And that's a very, 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 very important conceptual understanding to have. And if students don't have that, then they get locked in on the numerals and then subtraction gets really hard. You ever notice how subtracting is harder than addition? The reason that's difficult for most students is because they don't have a good understanding of what these things actually mean. They're really good with moving symbols around, but then when you ask them to do it without symbols, ask them to do it in their head, they can't because they need the symbols. Because all they've been doing is pushing the symbols around, not thinking about this type of stuff, not thinking about the actual concepts that we're talking about. So, subtraction is always an act of taking from. It's always taking from. Notice that this is different than addition. Addition, you're starting with two quantities and bringing them together. With subtraction, I'll do it like this. With subtraction, you are starting with one quantity and then removing something from that quantity. There's a difference. I didn't start with two quantities. I started with one quantity. Here's my one quantity, 3 in this case, and I'm going to subtract 1. And when I subtract 1, I'm taking that amount away from the quantity that I had. That's what subtraction is, okay? And in any situation where you ever do subtraction, ever in any scenario in your life ever, you should always be able to represent that process as taking from. Always, always, always. Okay? Keep that in mind for when we talk about how to model these things. Oh, there you go. How can we model these ideas? How can we model these ideas? I've essentially shown you the physical way of doing it, right? Now we just have to figure out how we can draw that as a picture. Addition is bringing together, subtraction is taking from. Okay, so let's talk about modeling addition first, and we'll see a few different models, and then we'll talk about subtraction. So first off, let's look at the set model. The set model is literally a pictorial way of describing what I did with my hands in the video right here. I had two quantities. I had this quantity, and I brought them together to make this single quantity. That's addition. How you do this, or I shouldn't say how you do this, how you draw the picture is a little bit flexible, and this is what's kind of nice. The one thing that your picture does need is it needs to somehow demark one collection of objects and a second collection of objects, and then it needs to show those two collections being combined into a single collection, or any number of collections, as we'll see in an example here. That's what you need to do when you're trying to model addition. Notice I'm not abusing any of those operation signs, the operators. I'm not abusing the addition sign. I'm not just doing this. And this is a common mistake that students will make in the beginning. I'm not just putting a plus sign and then saying 2, 3, 4, 5, 6, 7, right? That's not a way of modeling. Actually, let me emphasize this for a moment. Let's talk about this for a moment. What is wrong with this picture? If I'm trying to model the sum 4 plus 3 equals 7, what is wrong with this picture that I'm going to highlight in red up here? What's wrong with that picture, do you think? Go ahead and just take a moment to think about it. What's wrong with that picture? That's a good question. What is wrong with that picture? Okay, now let's talk about it out loud. What do you think? What do you think? Any ideas? Well, the idea here is that in this picture up here, all you haven't modeled anything. You just rewrote 4 plus 3 equals 7 using a different picture. That's all you did. You did using a different system, using a different numeration system. Look, there's no difference between what I drew above this red line and what I'm drawing down here, plus 4 equals 7. Except in the top, I used this. Oh, what am I doing? I swear, sometimes I feel like I'm dyslexic. Let me go back. 4 plus 3 equals 7. Up here, all I did was write 4 as 4 dots, and down here I wrote it as the Arabic numeral 4. Then I wrote plus. Up here I wrote 3 as 3 dots instead of the Arabic numeral 3, and then over here I wrote 7 as 7 dots instead of the Arabic numeral 7. I haven't modeled anything. I haven't modeled anything conceptual at all. All I did was rewrite the same sentence with a different language, essentially. That's all we did. No modeling has gone on. So that's why it's critically important, one second here, critically important to have something that looks like this. Something that looks like this for the students, showing the act of addition. Okay, let's do a couple examples. Let's do 8 plus 7. And it's not too difficult, not too fancy. If I wanted to do 8 plus 7, what I would probably do is I would draw 8 dots. I'd probably draw them in some sort of meaningful collection, like 8 is the same as 2 times 4, so that might be nice. And then if I'm going to add, what was it, 7? Here we go. Okay, and I might even say this. This is the quantity 8, and this is the quantity 7. Notice I'm just representing those quantities in two different ways. But the addition part comes from me taking this quantity and adding them together. What do we get? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is the quantity 15. And then I'm going to link those like so. That's the set model. What I'm showing is that if you take 8 objects and combine them with 7 more objects, then you have 15 objects altogether. And we would write mathematically 8 plus 7, make that a little cleaner. 8 plus 7 equals 15. That's the idea right there. Okay. How about this one? Let's do 3 plus 4 plus 5. The model is pretty much the same. You just got to show that bringing together. So let me go ahead and do that one here. And then I recommend that you practice the other ones. Practice these ones on your own. Try to do 2 plus 10, and then try to do 1 plus 1 plus 1 plus 4. But we're going to do 3 plus 4 plus 5. So I'm going to model the quantity 3 with these 3 dots. I'm going to model the quantity 4 with those 4 dots. And I'm going to model the quantity 5 with those dots. I'm going to group them, and then I'm going to bring them together. And 3 plus 4 plus 5 is 7 plus 5. Is that right? 7 plus 5, which is 12. So down here, I'm just going to draw 12 dots. And I'm going to bring them all in. And now I've shown that 3 plus 4 plus 5 is equal to 12. There we go. So that's how you would do it. So go ahead and practice that on your own a couple of times, and it should click pretty quickly. Okay, so now let's talk about the number line model. The number line model is also fairly straightforward, but there are some subtle caveats. So let's check out these examples. This is modeling the operation 4 plus 3, which is equal to 7. Now there's 2 ways to do it. One way to do it is to, actually, no, I'm sorry, I'm thinking of something else, my bad. This is how you would do it. You're gonna start at 0. That's what's going on right here. Start at 0, and then you're gonna add 4, and then you're gonna add 3, plus 4, plus 3, like that. And in doing so, you end up at 7. So that's how you would model addition on the number line. Okay, 4 plus 3 equals 7. Let's do a couple right here. I'm going to do, let's see, we'll do 8 plus 7 and 3 plus 4 plus 5 again. Okay, so here's, I'm going to need some space. I'll just keep it like this. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You don't always need to include these, but I need another one. 15, I'll put another one up here. You don't always need to include all of those tick marks, just as many as you think your students will need, and as many as you need to convey the idea that you're trying to say. Oftentimes you won't need all of them. Okay, so we're doing 8 plus 7. So let's do it this way. First, we're going to start at 0, and we're going to add 8. Okay, and I'm actually going to write up here plus 8. And the next thing I'm going to do is I'm going to add 7. And I'm going to write plus 7. And then where I landed was 15. So now we know that 8 plus 7 equals 15. And that's how you would do it, basically like that. The other option is you can already start at 8 and then add 7, but I feel like this makes a little more sense. It makes a little more sense for students. There's one important caveat, and I'm going to tell you this right now. We're adding 8 and 7. We're not adding 1 plus 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 1. So students have a tendency in the beginning to want to count every single step in their model, but that's not correct. That's not modeling the right operation, and I'll explain why in a minute. This would be an incorrect way of doing it. So I'm going to write it in red. Basically, don't do it this way. Don't go 1, 2, 3, 4, 5, 6, 7, 8, plus 1, plus 1, plus 1, plus 1, plus 1, plus 1. Okay, and then 1, 2, 3, 4, 5, 6, 7. Yeah, you don't want to do it like that, because now you're not modeling 8 plus 7. You're modeling 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. We want them to be able to actually make those leaps. We don't want them to have to always count up, and we'll talk about that in just a minute too. We don't want them to always count up in that way. So that's the idea. And now let's take a look at this one down here, 3 plus 4 plus 5 instead. Let me do this. There we go. Nice. Okay, so let's do 3 plus 4 plus 5. I'm just going to move this down here. And it's the same kind of deal. I'm going to use pink because this is the way you should model it. We're going to start by adding 3, and then we're going to add 4, and that's going to take us to 7. And then we're going to add 5, and that's going to take us all the way up to 12. So we know that 3 plus 4 plus 5 equals 12. That's the idea. So that's how we would model with a number line. And now hopefully you can see why it's so important to actually mark the actual steps that you're taking, right? It's important to mark the actual steps, not to just count ones, right? That's a different addition if you're counting a bunch of ones. All right, so try to do some examples on your own. Try to do these ones, try to do these ones, make up some of your own problems, play around with it as much as you need. It's not too bad, right? Um, okay. Oh, I did the lines right there. Just a blank slide. So here are some addition strategies that we'll teach our students when they're pretty young. One of them is called counting on. We're trying to get these students to be able to count in a meaningful way. And an easy way is to just count up with your fingers, right? We've all done this. What is 6 plus 2? You start with you start with 6, and then you go 7, 8. So you count on. That's called counting on, going from 6 to 7 to 8. Doubles. So if a student has doubles memorized, they can make a really good use of them. So for example, 5 plus 6 can be viewed as 5 plus 5 plus 1, which is really 2 5s and then 1 left over. This is a really, really powerful thing. And what you'll notice in these slides and in these techniques, a big skill that we're trying to impart on our students is breaking numbers apart in meaningful ways and combining them in other ways that are meaningful. And that's what's going on right here. You know, think about the emotional component. Think about how you feel when you see 5 plus 6, right? How do you feel? It's pretty small, so it might not feel too bad. But what if you had to do something like 25 plus 6? We'll just say that. Now, how you add that in your head depends on who you are. But if you can recognize that you could just go ahead and take 5 and give it to the 25, and then you've just got 1 left over, then it's a lot easier to compute. And the only reason that I know that I can do that is because I understand what these symbols represent. They represent quantities. They're not just symbols to be pushed around, right? That's the idea. Making 10, this is another very, very powerful one. Make 10s get to these benchmarks. 10 is what we call a benchmark. And then you can count up the rest of the way. So 7 plus 6, well, let's take 3 from 6 and give it to 7. And then we've just got 3 left over. So we made a 10, and then we have 3 left over. This is also appealing to our decimal system, right? It's appealing to the decimal system. How could you represent this using linking cubes? Well, you can take 7 linking cubes. I think I have enough here, actually. Let's do it. Here, let's do this one together. 1 second. All right. I think I have enough. Maybe I don't. Do I? I don't think I do. Oh, no, I have one too little. I don't have any more on me. Oh, well. But you get the idea. Let's see. Here we have 7. So here's 7 linking cubes. And then we would need 6 more. So pretend I have 6 here. Pretend I have 6 instead of just 5. Okay, so here's 6. You can't see the 6th one, it's in my hand, right? And what I'm going to do is I'm going to try to add these two quantities together. And remember, addition is just the act of bringing together. Now they're together. But how much do I have now? Well, what I can do is I can make 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 3 left over. I have 3 in my hand. Trust me, I have 3 in my hand. There you go. So I've made 10. All right. You can also count back, and this is extraordinarily helpful. I encourage you to all practice this technique. And we'll see some videos of this. We'll see some students using this strategy in just a few minutes, actually. It'll be a good time to pause this video and take a break before you watch the rest of it. So let's say you wanted to do 9 plus 6. 9 plus 6, that's too hard. 10 plus 6 is a lot easier. So let's do 10 plus 6, but then remember that we added an extra 1, so we need to take that 1 away as well. That's what we're doing here. 10 plus 6 is easy. That's 16. But that's 1 too many than I need. Oh, forgot to transition back. Sorry, go back here. Let me try this again. 9 plus 6. 9 plus 6 right here. Too hard to do? Change it to 10 plus 6. But then remember that you've got to take away that extra 1 that you added. So then you end up with 16, take away 1, and that's 15. All right. How about this one? This is a good question. A student computes 69 plus, or 68 plus 29 by saying you can take 1 away from 68 and give it to 29. So you get 67 plus 30, which equals 97. Okay? That's what a student tells you as the teacher, all right? My question is this a valid method? Or did the student get lucky? What do you think? Go ahead and think about it for a minute. Is that valid, or did the student get lucky? I think I have an idea. Go ahead and try to talk out loud to your group and see what they have to say. Okay, well, you might be able to tell that it is actually valid, but how would you know for sure? Who says? Don't take my word for it. Don't believe anybody. Don't believe your student. Don't believe your boss. Don't believe anybody, right? How do you know that that's actually a valid method of adding? Well, if it's valid, oh, I thought I had that written here. Yeah. If it's valid, then you should be able to express it mathematically. You should be able to show with a chain of true equalities that that is actually a valid method of computing. And that's what we're going to do right now. We're going to show that that is actually true. Okay, so the student is starting with 68 plus 29, and they're manipulating that expression to get 67 plus 30, and then they're adding that to get 97. So we should be able to show that they can start here, manipulate it to get there, and then finally end up with 97. That's what we're going to do right now. So 68 plus 29, and then the student says to do this. Take 1 away from 68 and give it to 29. So what I'm going to do is this. Oops. I'm going to take 1 away from 68. Just like that. So I broke 68 up into 67 plus 1. Now I can reassociate. All right? And that gives me 67 plus 30, which is exactly what our student got as well. And then last but not least, that's 97. There we go. Nice, we did it, right? So this decomposition, this sentence that I've written here is extremely important, and you'll have to do this on the activity and also on the assessments. This is how you verify that a student's calculation is actually mathematically valid. If you cannot write down a sentence like this, then you can't guarantee that what they've done is valid. So that's why this is an important skill for a math teacher to have. The other thing I want to point out is a couple things, actually. One, that period at the very end. I put that period because I wrote a sentence. As weird as it looks, this is one big run-on sentence. That's really all it is. It's a big run-on sentence. I'll read it out loud in English. It's really, I mean, it's an English sentence, but I wrote it in math. I'll read it out loud, and this will be like the only time I'm ever going to do this, okay? So here we go. You ready? I'm going to read this sentence out loud. This sentence says, 68 plus 29 is the same as 67 plus 1, then adding 29, which is the same as 67, then adding 1 plus 29, which is the same as 67 plus 30, which is 97. There we go. That's my long run-on sentence. But who wants to say that every time? And I certainly wouldn't want to have to write that out in English words, you know what I mean? So we write math instead. But that's what it is. It's a big run-on sentence. And like I had said in the previous lecture, these numbers are your nouns. These are your nouns right here. All these numbers, these are your nouns. And then the plus signs and the equal signs, those are your verbs. They're telling you what's happening to the numbers, right? Although I should be careful saying that because the equal sign is not an operator. So I had talked about that before, but the equal sign is not something that operates on anything. It's more of like a connecting word. It's the if you know enough about grammar and how the word be is kind of a passive verb, that's what equals is. It's kind of a passive verb. It's saying 68 plus 29 is the same as this. That's it, sentences, right? Okay. So that's it for addition. Now let's talk about subtraction. So this is the take from model. And this is, in my opinion, the most important model for students to have. Notice that there's a difference between the set model for addition, right? We're not starting with two separate quantities and then combining them. It's not that way anymore. We're doing subtraction. We're starting with a single quantity and we're going to take something away. That's the difference. That's the take from model. So this is a perfect interpretation, or sorry, this is a perfect representation of 8 minus 3 and how that's equal to 5. So I would actually put it in a second step, but it's not terrible. Notice here in the big circle, the circle that's in black right here, we've got the quantity 8. And what we're going to do is we're going to reach into that quantity and we're going to select 3 of those blocks and we're going to pull them out. This is the act of taking away 3. There's illustrating the removal right there. We're illustrating the removal of those 3 objects. And then what's left is 5. And so that tells you that 8 take away 3 must be 5. All right, that's the idea. Okay, so let's do a couple here, and we're going to do it in a couple different ways, actually. So let's try 12 minus 5. Let's do that one first. So I'm going to start with a quantity of 12. Just need 12 dots, let's say. 1, 2, 3, 4, 5, 6. Actually, I want to give myself some space. Scoot that over. 7, 8, 9, 10, 11, 12. So I'm starting with 12. And then what am I taking away? 5. Now what I need to do is I need to reach in here and find 5 of these objects. And then I'm going to take them away. Taking away 5. That's what it is. There's the takeaway act. And now how many are left? And what I usually do is I usually like to write an arrow that looks a little bit like that, or some kind of an arrow that's a different color or bold, indicating what happens after that removal. And what's left is 1, 2, 3. Actually, you know what? Just to make it even clearer, I'm going to stick with the same format. 1, 2, 3, 4, 5, 6, 1. And what are we left with? 7, right? Yeah, 7. There we go. So you could even come in here and write, for example, 12 minus 5 is equal to 7. And this is the picture. This is the picture that you would draw, something like this. That's really all it takes. But it's very, very, very important to include this part, the actual act of taking something away. You have to show that physical act of taking something away. That's how you model subtraction. Let's do another one. Let's do, you know what? Let's try this. Let's do 21 minus 8, except this time I'm going to use base 10 blocks. Let's try that. Who says that we have to use dots? We can use base 10 blocks. So let's try to do that here. Remember, those base 10 blocks are just ways for us to represent quantities, and now we're operating on quantities, which means that we should be able to operate on those base 10 blocks in a meaningful way. Check it out. So what are we doing? Which one? 21 minus 8. So let's model 21 using base 10 blocks. There's the quantity 21. Now what I need to do is I need to be able to take away 8. But there's a problem. I don't have 8 individual pieces to take away. I can't do it yet. So what I need is I need an intermediate step. I need an intermediate step where I go and I break apart a 10, and so that way I have 10 ones to actually pull from. So I'm going to go ahead and draw a little arrow here. Let's go this way. And then we'll say 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. This is still the quantity 21. I haven't done anything. I just broke up a 10 into 10 ones. Now I can reach in and take away the 8 that I needed. All right, where are those 8? How about this right here? Taking away 8. All right, and then lastly, I'm just going to put one more picture at the end here showing the result. What's left? We've got 1 long and then 3 ones. This is the quantity 13. So is that right? I don't know. Notice how I didn't even actually do the calculation? I didn't do the calculation. The model led me to the answer. That's the whole point. I don't know. So here I believe I've modeled that 21 minus 8 is equal to 13. Is that correct? Well, 20 minus 7 is 13, and then I've got 21 minus 8, so that does work. That does work. That's actually a technique we'll talk about in a minute here. But the thing I wanted to emphasize is that, oops, that. The thing I wanted to emphasize is that I didn't know the answer. I didn't know the answer. I didn't know what 21 minus 8 was. I didn't have the answer calculated in my head. I was just doing the model. And in doing the model itself, sorry, I guess I should go this way. Doing the model itself, I got the answer. And that's what you have to remember. That's what your students are going to rely on. Your students don't just know the answer like you as an adult do. They need the actual model to do it. The model is going to give them the answer, not the other way around. It's kind of like with calculators, right? The mathematics existed before the calculators. So we could do the mathematics before those calculators existed. And it's the same thing here. Your students need the model to get them to the answer. They need the model to get there. They're not going to go the other way. They're not going to have the answer and then make the model. So when you're doing this, just uh, try to be wary of the fact that you might accidentally be working backward in this sense. And in this sense, that's not a good idea. Or wait, working backward. Anyway, okay, so that's how you would do it. Okay, now let's talk about the number line. The number line is also fairly simple. In this case, you have a couple options. You can start at 0, and you can count up. So we're doing this right here. 8 minus 3 equals 5. You could count up to 8, and then count back by 3. I would say take away 3. That's one way to do it. Another way to do it is to just go ahead and start at 8 and then take away 3. And then where do you land? Should have squared that one over there too. So that's pretty much all it is. The same rules that I said before about addition apply here. You can't, you don't want to do a bunch of like subtracting of ones or anything like that. You don't want to keep doing minus 1, minus 1, minus 1, minus 1. You want to do minus 3, right? Minus 3, one big chunk. Okay, let's do a couple examples. These are pretty straightforward. I'll just do a couple. Here we go. I'll do 12 minus 5, and I think what I'm going to do is actually start here. Okay, and I'm going to do the first method. So what I'm going to do is I'm going to start at 12, and I'm going to take away 5. And when I take away 5, where do I land? Right there. So this is me taking away 5, and I land on 7, which is my final answer. So 12 minus 5, that's equal to 7. There we go. 12 minus 5 is equal to 7. And like the previous example showed, you could start at 0 and then go up and then go back. It's totally up to you. Totally up to you. 21 minus 8 is about the same, so I think that I'll pause here and I'll let you guys try some of these examples on your own. So this is actually here. I'll do this just to get everybody to think about it. How would I model this? Let's try it out. Okay. Now, modeling to, oh, that's just a blank slide to try it out. Okay, last couple models here, and then I think we're getting to the videos. Yeah, we'll be to the videos in a minute, and that'll be a good time to pause. So there's another model called the unknown addend model, and this is another one that we teach children, and it's also very intuitive. Here's an example. 5 balls are on the table, 3 are red, and the rest are green. How many balls are green? So the way that this question is modeled is like so, right here. The question is actually modeled like this. You know the total. You're given the total sum. You're given one of the addends, and the question is, what's the other one? What's the missing addend? What's the unknown addend? Now, this is mathematically equivalent to computing 5 minus 3. That's what this double arrow means. Double arrow in that way means equivalent. So we're getting students to think about subtraction in an additive way, right? Essentially, they're saying, how much do I have to add to 3 to get to 5? Well, the answer is 5 minus 3. That's the answer. That's the question mark. Oh, another model is called the comparison model, and this is a really good one for children, and you can do it with strip diagrams, with objects, with anything, right? So let's say Henry has 2 dandelions, and Galilea has 5 dandelions. How many more dandelions does Galilea have than Henry? Well, now we're looking for this space right here. You can almost see that it's a strip diagram. It's like begging to be a strip diagram, right? I mean, as a strip diagram, you would pretty much just do this. There you go. Now it's a strip diagram. I just filled in the blanks, right? And we're looking for this question mark. That's the comparison model. That's a way of doing subtraction, especially if you're mostly comfortable with addition. It's really, really nice. Okay, so moving on here. Story problems that have an additive or subtractive structure are called additive story problems. Children in grades K through 2, so you can think about 5-year-olds up to 8-year-olds. They should be able to model and solve all types of additive story problems using the models that we just learned right now. The set model, the number line model, the missing addend model, and the comparison model. So by the time a student leaves grade 2, they should be able to work with those very, very, very comfortably. Very, very comfortably. Solving story problems. Direct modeling involves acting out the information given in a problem. This is a term that the book uses, so I like to toss it in here. And this is the big point. And this is, I think, where we're about to watch these videos. But this is a good segue. So if you would want to like have an intermission or take a break here, there's a profound difference between being able to add and subtract and being able to manipulate mathematical symbols to express the act of addition and subtraction. This is the key thing. See, in the old pedagogical model from back in the day, back when I was in K-12, if a student was unable to perform the subtraction algorithm, you know, this one where it's like, oh, like, 12 minus 9, and you'd have to like, oh, this one doesn't work, right? So you'd have to go and like, so you're supposed to do something, like you break this apart, and now there, oh no, now there's a 0, but then this becomes a 12. Oh, but wait, did that help me at all? Huh. Anyway, it's 3. So in the past, if a student was unable to regurgitate this model, or this algorithm, I should say, they were deemed as being unable to subtract. But hopefully now you can appreciate that that's not the case, or not necessarily the case at least, right? It may be the case that a student can add and subtract totally fine, but this particular algorithm is really confusing to them. Maybe it was introduced poorly, maybe something along those lines. But the point is, just because they can't do the algorithm doesn't mean they don't know the mathematics behind it. And vice versa. Just because they know the mathematics doesn't mean that they know how to do the algorithm. So you have to be very careful. You have to distinguish between a student's mathematical ability and their ability to push symbols around. And you got to hope that they're not locking themselves into pushing symbols around. And you'll see that if students are not taught to just manipulate symbols, they can use their own imagination to solve these problems. And that's what we're going to watch in these videos coming up right now. 1 second here. Yeah, okay. So the first thing I want to say is now's a good time to pause. We're going to watch a couple videos. They total about 5 minutes altogether. Wait, a little longer, like 7 minutes altogether, but I'm going to give some commentary and look back at them a little bit. So if you want to take a break, now's a good time to go take a break and then come back to watch some videos of children adding and subtracting. And while you're taking your break, I'm going to have them set up here. All right, so let's go ahead and see this first video here. This is James, and James is going to be doing a computation, and just watch how he actually computes this problem, okay? Mm, 1 second, the audio is not quite playing. You have to pause for, just give me a minute here. Come on, audio, what you doing to me? 1 second. try this really quick. There we go. Okay, let me back this up. Just one more minute. Let's start over here and let's see what James is about to do.
James had 61 stickers. He gave 43 of them to his friend. How many stickers does James have left?
I came up with 18.
Okay, how'd you get 18?
Well, I had 1, and I took away 3 from that, and I came up with -2.
Okay.
And then I took the 40 away from the 60, and I came up with 20. And then I had to take away 2 from 20, and that equals 18. So I did it that way.
Okay, good work. That strategy that you just did with the negative numbers, how'd you learn that?
Well, I just kind of played around with math, and somehow I just thought about our negative numbers we were talking about in class that one day. And I thought that if I had 1 and I took away like 5, that I could just write -4 on the side and just remember to take away 4.
Yeah, very, very good. Very good. So did you all see that? He came up with his own way of solving that problem, essentially. Actually, I kind of put it right here if you're watching. We're going to skim through it in just a second. But for one, notice that he didn't really bother aligning anything. He didn't bother with trying to like line these up. The one thing he did do was he lined up these so that the tens and the ones were in the same column. And then he boxed the ones. And then over here, he wrote 2 minus. One thing I want to point out here about children when they first learn these things is they will often write negatives and positives on the wrong side because they're still learning how to read and write. They do that stuff all the time. But does it really matter that he wrote the negative sign over here? No, it doesn't, because he remembered that that's a -2. And so what he did instead was he added the 60 and the 40, the 60 and the 40, and he said that that was 20. That's what he's got right down here. Then he wrote this 20, right? But that's 60 plus 40. Now he has to account for this bit right here, the 1 minus 3. And 1 minus 3 is -2. So he went and said, okay, well, it's not 20 because I have to include the -2. But if I add -2 to 20, then I get 18. And that was the idea. And notice that, again, there's so much flexibility here. It didn't matter where he wrote the numbers or how he wrote the numbers. He knew how to do the problem. He knew everything. Really great. Okay, so now let's see a different one here. Let's see. Hold on one second here. Let's see Joel now. Oops. Hey, what are you doing? What are you doing? Sorry, give me one second. OBS is picking the wrong screen. Joel, where did you go? There we go. Okay, so let's check out Joel and let's see how he solves this problem.
Max had 44 comic books. For his birthday, his dad gave him 19 more comic books. How many comic books does Max have altogether?
63.
Okay, how did you get 63?
4 plus 10, 40 plus 10, I knew equaled 50. And 4 plus 9, I knew that would equal 13. And 13 is 3 more than 10, so I knew I would have 63.
Nice.
Pretty cool, huh? He figured that on. I figured that out on his own. That was another really cool one. And the thing I want to point out here is that he was. Wait, let me go back to the slides really quick. Here we go. He was specifically looking at place value and understanding our numeration system to solve this problem. And the teacher asked him to explain how he figured it out. Did you catch that? At the end, she was like, "Can you explain how you did that?" That was one of the Common Core standards, right? Students should be able to explain why a process is true at the level of their own mathematical maturity. He's very mathematically mature here. He very much understands our numeration system. He understands what addition is. He understands how to break numbers apart into meaningful chunks. That's the type of power we're going for. Mathematics is just an incredibly powerful tool. But just to emphasize what he did, let me actually make this a little bit bigger, was he noticed that he had 40 plus 10, and he said that's 50. And he did that in his head. Notice that he didn't write anything down because he didn't need to. He was just like, oh, that's 40 and that's 10. 40 plus 10, that's 50. Then he went to the ones and he was like, okay, 4 plus 9, that's 13. And then he was like, okay, 50 plus 13 is 63. And he's like really excited when he says it at the end, right? 63. Exactly. Good job. Good job, Joel. Okay, so let's try the next one. Let's see Kate. Give me a second to get the video set up here. Where are you, Kate? Where are you, Kate? Oh, wrong one. Ah, there we go. Okay, so let's see how Kate solves this problem right here.
Kate has $29. For her birthday, she got $62. That kind of be neat, wouldn't it? How much money does Kate have now?
Well, 6 plus 2 is 8, and then 89, 90, 91.
So how much money do you have now?
$91.
Okay.
All right, let's pause there for just a second and kind of look at that one. That was quick. That was quick. She figured it out quickly. But the problem she was trying to solve was 29 plus 62. And if you listen carefully, she starts by, again, adding the tens and then adding the ones. And then what I really love is that she even counts up to get to the final answer. Let's just play it back one more time to see. Check this out.
Kate has $29. For her birthday, she got $62. That kind of be neat, wouldn't it? How much money does Kate have now?
Well, 6 plus 2 is 8, and then 89.
So pause right there for just a second. She said 6 plus 2, but she remembered that it's actually 60 plus 20, and she said 80. And then she went ahead and said 89. So she actually did 60 plus 29 in her head because that's easier to do, right? I can't do 62 plus 29 in my head, but you know it's easier to do 60 plus 29. Because what's that? 60, 89. And then what does she do?
90, 91.
90, 91. She counts on. So she gets to 89, and then she knows there's two more to add, and she just counts up by 2. Just using all of the tools, right? All of the tools.
So how much money do you have now?
$91.
Okay, nice work.
$91. And she's really excited, which is really cute. Okay, let's actually see her do a different one. She's going to solve a different problem here. Let's check it out. Oh, also notice that she's in 3rd grade, so the numbers are double digit, a little bit large. And we're going to see here, I think, an even larger number. Let's check.
Andy has 312 books. If he donates 147 of them to the library, how many books will he have left?
How many does he donate to the library?
147.
Okay, fee. Okay, you can't take 7 away from 2, but it'd be, see, 7 take away 2, 7. So it'd be -5, because you could take away 2, but then there's 5 left over. So it'd be -5. 4 take away 1 would be -3, because you could take away the 1, but not the whole thing. So it'd be 3. And then 5 and 3 is 8, so it's negative, or no, it's -35. So it's -35 so far, and then 300 take away 100, it'd be 200, and then, but 200 take away 35 would be 100. Would be 165.
Nice work.
Yeah, very nice work, I would say, right? So she actually computed that to get 165. And again, you notice that she didn't actually write anything down. She didn't write anything down. What she's doing is she's using place value, and she's using our numeration system, and she's using her numeracy, her ability to work with numbers, not just the symbols, but she's thinking about what those are in her head. And she also appeals to the negative numbers. Did you happen to catch that she wrote the negative sign on the other side again? Where is that? Right somewhere back here. Yeah, right over here, she wrote -35 as 35 minus, which is fine. Did it matter? No, it didn't matter. And that's the whole thing. It doesn't matter like exactly the structure they write these things down. These algorithms are just tools. They're tools for them to use. They learn how to wield them in their own unique ways. It's really, really fun. But if you listen, she was appealing to place value. And she first worked on the hundreds, and she said, oh, that's going to be 200. And she didn't even write it down. She just kind of collected it in her head. She was like 200 over here. And then she did the tens, and she came up with -30. So I'll write that over here. Actually, let me blow this up a bit. There we go. And then she essentially did -30, and then she did -5, although she wrote -35. But then when you add all these together, what do you get? Do it in pieces. You don't have to do it all at once, right? Just do it in pieces. Actually, I forgot to do this. There we go. Well, 200 minus 30 is 170. And then you still got to take away 5. And there it is, 165. So you can see, like, compare this process to trying to do the same subtraction problem with the standard algorithm. In fact, maybe we should do it right here. Let's see what it looks like when you compare. Oh man, I don't even know if I want to do it right now. Okay, I've got to do, okay, so I can't do 2 minus 7, so I've got to go and try to take something, borrow, I guess. I'm borrowing. I don't know how to do this, right? It's just too convoluted. I don't know what I'm doing. Okay, I guess that's going to become a 0, and that becomes a 12, I suppose. And now I can do 12 minus 7, and that's 5. Okay, but now I can't take 4 objects away from 0, supposedly. That's what the book told me, right? So I got to come over here. That becomes a 2. And now I guess this becomes a 10? What does that become? A 10 or something? I guess it's a 10 now. That's kind of weird. I suppose it's a 10. And then I subtract 4, and I get 6, and then 2 minus 1 is 165. So which process made more sense to you? This one or this one? Think about it. That's what we're talking about. That's what we're talking about, okay? All right, then let's see one more video from Rita. Let me get it queued up here. All right, Rita, let's see what you're going to do. Third grade.
Lucy had $38. One weekend she earned $25 raking leaves for the neighbors. How much money did Lucy have then?
Well, you could take the $38 and make it $40.
Okay.
And then 50, 60, 65. But you have to take away the 2. So that's 63.
Okay. Good job.
Whoa, did you see that? Did you see that? We got to watch that one again. That's just too fast. I don't even remember the problem. She was so fast. Okay, let's let's do that one slowly. Okay. Try again, Rita.
Lucy had $38. One weekend she earned $25 raking leaves for her.
Okay, so she's computing 38 plus 25. That's what she's trying to compute.
The neighbors. How much money did Lucy have then?
Well, you could take the $38 and make it $40.
Okay.
Boom. So first off she was like, I don't want to have to deal with 38. 38's too hard. Let's just deal with 40. So she was like, let's just rewrite that as 40.
And then 50, 60, 65. But
50, 60, 65, right? So what is she doing now? She's splitting this up and adding it in chunks. She adds 10 and then 10 and then 5. So she basically goes 50, 60, 65. Oop, come back here. 60, 60, or sorry, 50, 60, 65. And then what does she say?
you have to take away the 2. So that's 63.
You have to take away the 2. So remember, when she went from here to here, she added 2. So now she remembers that she has to take away that 2 at the end, and she does that right at the very end and then says 63, and there it is, right? Let's just hear her finish it off, just for brevity.
So that's 63.
Okay. Good job. I understand just what you did.
And so do we, right? Just amazing. I think it's just really amazing. Okay, so that's the last of the videos. Let me go back here. One thing I want to point out is this before we almost call this a day here, before we look at the activity. Notice how each student used place value and number sense to solve the problem, not a rote algorithm. That's key. That's what we're trying to build with our students, okay? All right, so now let's play. Where did that come from? Get out of here. Let's play. So let's go take a look at activity 3A really quick. Let's talk about it so that you know what to expect. Let me change the size of my pen here. All right, give me 1 second. All right, activity 3A. This is all about addition and subtraction and modeling addition and subtraction. So here's what you're going to do. First, you just need to illustrate this using the set model. That should be very straightforward. Then you need to illustrate this using base 10 blocks. Also very straightforward. If you need, I will happily go over as many examples of this as you want. You just got to ask, and I will do it right in the collaboration meeting. And again, if you can't make the collaboration meeting or if something comes up, the opening, the beginning is recorded, so you can watch it later. I'm trying to give you as many resources as I can. Then you're going to do this using the number line model. It's also not too bad. Then this is an important one. So I did an example of this earlier in the lecture, but this is where a student is telling you how they computed something, and you need to demonstrate that their method is valid by writing a chain of true equalities. That's what you have to do here, okay? Illustrate this using the takeaway model. Have to show the taking away process. Illustrate this using base 10 blocks and the takeaway model. Notice there's going to be a difference here. So notice the calculation is still the same, but the picture that goes here should not be the same as the picture that goes here. So keep that in mind. Show this subtraction using the number line model. And then same thing. This is another one of those times where you need to write a chain of true equalities that begins with this, shows them doing this, and then ends up with the correct answer at the end. All right, so that's what you're doing with that activity, and that's it. Again, I know this was a quite a long lecture. Some of them are kind of long, some of them are kind of short, but thanks again, as always, for bearing with me. And I guess I'll leave it at that. Have a nice day.